We've spent a lot of time talking about the magnetic field already, but we want to come back and remember some general properties of the magnetic field. One thing to note is that in chapter 29, we're doing a lot of work with the magnetic field. There's 10 sections in this chapter. And when we learned about the electric field, we actually spent about 3 or 4 chapters, depending on how you count, defining all of those ideas. So in a way, we're just building on some of the ideas that we've already learned within the electric field scenario and now creating the magnetic equivalent. So let's just review quickly some of the basics of the field, and in this case, we're now talking about the magnetic field. So it's at all points in space. What that means is that in this picture, I've only drawn my magnetic field vectors in some places, but that doesn't mean at this point it's 0. At that point, there's a magnetic field too. And what you can note, because all of the magnetic field vectors look the same, that implies that this is a uniform region of magnetic field. Remember that when I show a vector like this, that's actually telling you about the magnetic field at that specific point. So it's at all points in space, and we'll maybe only draw a subset of them, but it expands out forever. It has strength and direction, right? Magnitude and direction means it's a vector. And note that we show that little hat. B vector is our magnetic field. So remember that if you want to talk about its direction and strength, it's a vector, draw it that way, use that notation, and always think, how strong is my field? Which way does it point? So that's just like the electric field. Last, when we introduced the idea of the electric field, we were trying to talk about the fact that two charges can exert forces on each other without actually touching. And the same thing is happening here, basically. That if I imagine my little compass needle, which is a little magnet, and the center is a pivot, so the whole thing can't move however it wants to, but it can rotate around, it's actually interacting with another magnet, some sort of cause of the magnetic field, and it experiences forces, but they're not in contact. So that's again why we're introducing the idea of a field, to allow multiple things to interact with one another, but to not actually be in contact. But now our magnetic field causes a force based on a pole. And note that if we have a north pole, the force and the magnetic field are parallel. So this is our north pole. On the other hand, our south pole and the magnetic field give us a force that is opposite. So south gives opposite, north gives parallel. And that was really similar with charges in that we had negative charges that gave us opposite for electric fields, and for the positive charges it was parallel. So we do have the same scenario here. So again, there are a lot of similarities between electric fields and magnetic fields, but there are some important differences too. So first, the magnetic field interacts with a magnetic pole. A magnetic field does not interact with stationary charges. So again, keep in mind that magnetic poles and charges are not the same thing, that the electric and magnetic fields are not the same thing. These are two separate ideas that have a lot of similarities, but are not interchangeable. So why do I say stationary charges? Well, very soon you're going to learn that magnetic fields are actually caused by moving charges. But yet, most of the time when we talked about electric fields, we were actually talking about stationary charges. So a charge that is just sitting there does not create a magnetic field, and it does not interact with one. So keep that in mind for your magnetic fields as well. Stationary charges do not interact. Lastly, your magnetic field goes in loops, right? Notice that this is what's happening with your B field. Now, why does this matter? Well, when you had an electric field, we would have a positive charge, we would have a negative charge, and we would always say, oh, our electric field lines start on one and end on the other, right? And so those were our electric field lines. Our magnetic field lines, we're usually going to see loops. And this is especially true with wires. And again, it's tricky if you say, but what about a bar magnet? Don't worry about bar magnets right now. There's again a reason that we're not talking about them. So whenever we're dealing with wires, we're actually going to talk about magnetic fields that are going in loops. It doesn't start or end on the wire itself, it simply goes around the wire. So please keep that in mind because that's really an important distinction, and it's going to be tricky when you just look at something like this. If you think you're looking at an electric field, this doesn't look very valid, but this is a perfectly valid magnetic field.